Alrighty, so domain and continuity when we talk about piecewise functions. So I'm going to start, since we're freshing on a Monday today, I'm going to start by just reminding ourselves what it would look like if I have a function that has a domain of all real numbers, right? Negative infinity to positive infinity, any x value in there is fine. Or if I had a function where maybe I had to break up my domain. I had something weird happening, for example, at +3. Okay. So there are a lot of different options I could write for A. Does anybody remember the types of functions we talked about that would have a domain of all real numbers? Mm-hmm. Exponential functions have a domain of all real numbers. So you could write a simple exponential function, or you could write a really complex exponential function, add in all the bells and whistles, right? Something like maybe -5 to the 1/27th of 3x plus 4 minus 15. Those are both going to have a domain of all real numbers. Anybody remember another type of function that's going to have a domain of all real numbers? What did you say? Oh, any polynomial, right? So something as simple as y equals x, or if I did negative 0.239 x to the 17th minus 5.1 x to the 4th plus 12, that's also going to have a domain of all real numbers. You guys don't have to write down like the super crazy ones. I just want to talk about it. Any exponential function, any polynomial function. Did we talk about anything else last week that would have a domain of all real numbers? Those were the two big ones, right? We also talked about logs, but those are not all real numbers. We also talked about square root functions, but not all real numbers. And we talked about rational functions, right? And those were also not all real numbers. For B, I can have all real numbers except for 3. That makes me think that I probably want to write a rational function for this one. For square roots, we had to be usually greater than some value or maybe less than some value. So it wasn't just a single value we had to exclude from the domain. It was a whole bunch of them. Same with logs. Our argument had to be greater than 0, which meant we were excluding a lot of values, not just one. So that makes me think, again, rational function here. Something where on the bottom of my function, I would have x minus 3. Now, maybe that spot is a hole, and so I've got x minus 3 on the top as well. Maybe it's a vertical asymptote, and I've got something different on the top. But both of those would give me a function whose domain was all real numbers except for 3. I can't have 3. Again, in the first one, since it would be a reducible factor, 3 would be a hole. In the second one, it would be a vertical asymptote, but they would have the same domain. Today, we're going to focus on the domain of piecewise functions. What's the domain of this piecewise function? So a couple things we need to be on the lookout for. For the domain for each piece that I'm given off to the side, are we defined everywhere? So we have a split, let's say for B, x is less than 0, and then from 0 to 3, and then greater than 3. For one of these at 0, do we have an or equal to? Are we defined somewhere at 0? Same for 3. Do we have an or equal to? Are we defined somewhere at 3? That's one thing I'm going to look for. The other thing I'm going to look for is, do I have any place where my function like skips values? So if we look at A, the first piece has a domain of x is less than or equal to -1. The second piece has a domain of x is greater than +1. We have a gap in there from -1 to +1. Did you see that? I don't have anything defined when x is 0. I don't have anything defined when x is +1. I don't have anything defined when x is half or when x is -3/4. I have a big jump there. I have a gap. I am undefined over the interval from -1 to +1. Anything greater than -1 but less than or equal to +1 is not defined here. Okay. So when I ask you what's the domain of this function, it would be from -infinity up to -1, and we are defined at -1. -1 is included in this first piece. And then anything from +1 on is defined. But I can't put a bracket at +1 because that's not included in the domain here. For B, I've got x is less than 0, and then 0 to 3, and then x is greater than 3. Do I define my function at 0 in some piece? Is there a piece that includes 0, a domain of 0? How about 3? Is there a piece that includes 3 in the domain? Yes, I've got or equal to 0 and or equal to 3 somewhere in here. My x is also defined for all numbers less than 0, all numbers between 0 and 3, and all numbers greater than 0. Well, that's all the numbers. Does that make sense? Everything less than 0, 0, between 0 and 3, 3, greater than 3, we're defined everywhere. So our domain here would be everything from -infinity to +infinity. B is defined for all real numbers. Our domain there would be all real numbers. What about C? Do we have any x values that are not defined, not included in the domain for either piece of our piecewise function? I have a split there at 1. That's where I move from one piece to the next. But 1 is included in the domain for that second piece. So this would, again, be all real numbers for the domain, -infinity to +infinity. Just to practice as inequality notation, that would look like -infinity is less than x is less than infinity. How about D? Now D, we start at -10, and we're going to end at +2. But everywhere between -10 and +2, do we have those x values defined? Do I have any values in there that are not defined? No, we're good everywhere, right? We have a split between the first piece and the second piece at -3, but we include -3 in that first piece. So our smallest domain value here would be -10. Our greatest domain value would be 2. Since we can be equal to -10, I'm going to put a bracket there. Just less than 2, so I'm going to put a parenthesis there. Okay, so I'm getting my domain out of my piecewise functions. And then again, just for practice, this would be -10 is less than or equal to x is less than 2, if you use that inequality notation. For E, I've got 5 different pieces here. So I want to check everywhere that I move from one piece to the next. Am I defined at -1? How about at 0? At 1? Yep. At 2, are we defined? Yeah. So I'm defined over each of those sort of transition x values. Our domain starts at -2 and ends at 3, parenthesis or bracket at -2. Bracket, parenthesis or bracket at 3, parenthesis, very good. So our domain is from -2, including -2, up to 3, and we're defined everywhere along the way. What would be our domain for F? All real numbers, very good. I've got a split here, x is less than or equal to -2, but since I'm equal to, I include -2 in the domain. And then -2 up to 2, but we're equal to -2 here, so that's also included in the domain, and then everything greater than 2. So this would be All real numbers, negative infinity to positive infinity. What about G? Except for, yeah, except for 0. 0 is not included in either piece. Our function is not defined at 0. So I would say negative infinity up to 0, it's a parenthesis, and then 0 to infinity, again, parentheses there. And then H is a little tricky. What's our domain for H? Mm-hmm. Mm-hmm. Okay, so X cannot be -2. I'm never equal to -2. X can also not be +2. We're never equal to +2. And then there's one more thing that makes this tricky. There's one more value that I actually cannot have. I want you to look at the function part. So this is 4. This is 4. That's defined over the interval. We don't have any problems there. What about this guy? It can't be 0. I told you that one was tricky. So I need to break one of those intervals up. Okay. So from negative infinity to -2, and this is all going to be parentheses. And then from -2 to 0, and then from 0 to 2, and then from 2 to infinity. What would I see at 0? This is a little refresher from last week. The rational function, so it's got to be a whole or an asymptote. What would I see there? An asymptote, right? Can I reduce x with anything on the top of that function? Nope. That means it would be an asymptote. Good. So the next thing we're going to talk about is the types of discontinuities that we can see. So we saw some functions that were seemingly like, well, their domain, I should say, was continuous. We also had some functions where the domain was not continuous. But for piecewise functions, remember that the domain being continuous doesn't mean that the graph doesn't have any discontinuities. Okay, so even in places where our domain, I should say, was all real numbers, that doesn't necessarily mean that we don't have jumps or holes or asymptotes, right? We just talked about that last function. We know it's going to have an asymptote in there. But those other places where I go from one piece of my function to the next, that's going to be the focus for the rest of today. What's happening there? How do I decide? So one option is to look at the graph. So for these first couple of examples, I've given you the graph, but you'll also see some problems where I'm going to ask you to graph it yourself on a calculator. So we'll talk about that in just a minute. But for example 2 here, I've given you the graphs. I've also given you the functions, right? And these should look familiar because these are the functions we talked about, A and B on the first page. So we're looking at, for function A, a whole big like gap in our graph here, right? From anything bigger than -1 until +1. So we're discontinuous over this graph, right? I have x values that don't aren't defined, don't have y values. I've got places that I don't like seamlessly transition from one piece to the next. So this is an example of a graph that is not continuous. And I'm not continuous over a whole interval. From -1, greater than -1, up to and including +1, we're not continuous. Most of the graphs that we're going to see, most of the functions that we're going to see, we're going to be discontinuous at one point. So we've got a whole section of this graph where we're discontinuous. I'm going to call this a jump slash a hole. I have a sort of a horizontal leap that we make here, but then I'm also undefined at this point when x is 1. So we call that a hole, we call it a jump. It's probably be maybe best defined as a hole. I'm not going to give you one quite like this on a test though. For B, we have something a little more in line with what we're used to seeing, right? So 5x when x is less than 0, 3 when x is between 0 and 3, and then x squared when x is greater than 3. Our domain here is all real numbers because I am defined at every value of x. I've got an open circle here at the end of my first piece, but then I define that point up here, right? And I've got an open circle here, but that x value is defined down here. So our domain for this one was all real numbers, but I do have discontinuities here. When x is 0, we have, does anybody remember what this one's called? That's a jump. And then when x is 3, what do I have here? Another jump. The next couple we're going to graph. So if you've got your graphing calculator, go ahead and pull that out. I'm going to tell you on your graphing calculator, it's not worth the hassle to try to define the intervals, in my opinion. If you want to do that, go for it. But we can also look at 1 and see what happens there if our functions line up or if they don't. I'm going to pull this up on Desmos, but your graphing calculator is fine too. I want to show you Desmos because that's the graphing tool that the SAT is going to use this year and from now on. So I just want you to see it. Even if you have your graphing calculator with you, you can still use that, but I want you to see this other one too. So the first part of my function is 3 to the x. The second part of my function is x minus 3 squared minus 1. So I'm going to go ahead and get that sort of bold version here. So here's my function. And then we have a change at 1, right? Our change is at 1. Let me make sure I said something correctly. 3 to the x, and then x minus 3 squared minus 1. And it's at positive 1 that change happens. Are our functions defined to be the same thing at positive 1? Do they intersect at positive 1? Yeah. And on Desmos, just so you can see, if you use, I believe it's curly brackets, it lets you do the piecewise. Oops. Now it's going to be mad because I used a parenthesis on accident. There we go. And then for here, again, I wanted to show you Desmos because it's also a little bit easier to do those piecewise functions there. So can we see how we meet up for those pieces if I do shift it to the pieces? Now, if you're on your graphing calculator, this is a little bit harder to do to define over those pieces. You can just look at when we have that x value. Do they have the same y? Do they meet up? Do they intersect at that spot? And ours do. So this guy is continuous. Let's look at number 2. I'm going to get rid of my graphs here and graph my next piecewise function. First piece is negative 3x plus 1. And my next piece is pi equals x squared. And then we're looking at negative 3 as our place where things either happen or they don't. Maybe an intersection there, a little hard to tell. So I'm going to go ahead and define in here. 3 plus 1, so this would be from negative 10 negative 3. And then for our other function, from negative 3 to x to 2. Are we intersecting? No. On your TI Inspire, graph each of these, find that point of intersection. You're going to see that the x value is not 3. Okay? It's not 3 for your point of intersection there. So that would be your way to tell. It's like negative 3 point something, I think. But that would be your way to tell if it looks close on your TI Inspire. Is that intersection happening so that my function is continuous? No. What do I see here instead? A jump. Okay, a jump. I'm going to move this out of the way. So that first one was continuous, and the second one we had a jump. When x equals negative 3, we had a jump. Okay. So we can use a graph. I could also look at the function itself. There is a way to tell without graphing if my function will be continuous or if it's going to have one of those discontinuities, if it's going to have a jump or a hole or something like that, or an asymptote. So for a piecewise function, right, and this is just a 2-piece function, but if I had more pieces, for a piecewise function, my first function is defined from A to B. My second function is defined from B to C. B has to be included in one of those domains. Okay, so it could be included in the first one like I have here, or it could be included in the second one. If you had more pieces, then F3 of X from C to D, make sure C is defined somewhere, and so on and so on. For this piecewise function to be continuous, then all values over the interval from wherever you start to wherever you stop, so over A to C, have to be defined. So you can't have any x values that are not defined, not included in some piece. And this is the big part here. If you were to look at the first function value of B and the second function value of B, they need to be equal. So even though for this particular function, B is not part of the domain for your second function, whatever that y value is should be the same as what you get here. If they're the same, that means you would have an intersection of those functions at that point. If they're not the same, that means you've got some distance between them. Maybe it's a big distance, maybe it's a small distance. But if these function values are equal, your graph is continuous. If your function values are not equal, it's not continuous. So if I take a look at my next function here, again, this guy should also look familiar because this is from that very first example. If I look at part A here, this is what we would call a step function. If I were to graph this, what I would see would be pieces that look like this. Looks like stair steps. Okay. If I look at the domains here for these different pieces of our function, the intervals over which these different pieces are defined, I'm looking at where we break, right? Where do I move from one piece to the next? And then would those function values be the same? So at -1, we're going from a function value of 1, but it'd be an open circle here, to a function value of 2 with a closed circle here. Is that the same? Are they going to meet up? 1 and 2? Remember, these are y values. So a y value of 1 and then a y value of 2. Is that the same? Are 1 and 2 the same? No, right? 1 and 2 are not the same. So my function values are different here. At 0, we're going from a y value of 2. So this would be the point 0, 2 if it were on the graph. Over here, this would be the point 0, 3. Is that the same point? No, it's different. And then the same thing's going to happen at every single one of these pieces. It only needs to happen once for my function to not be continuous, but it's going to happen every single time here. If I look at 2, on this piece, if it were included, it would be the point 2, 4. On this piece, which is included, it'll be the point 2, 5. I've got a gap there in those y values. So this guy is not continuous. At every transition in x value, I've got a jump. So I have jumps at x equals -1, x equals 0, x equals 1, and x equals 2. I've got those vertical jumps. For B, little bit less easy to tell for B. I've got a horizontal line when x is less than or equal to -2. I've got a parabola between -2 and +2. And I've got a line with a slant, not a horizontal line. A line with a defined slope there, a non-zero slope when x is greater than 2. First thing I notice is that I am defining x values at -2 and +2, so no holes that I can see here, but I need to check to see if I'm going to have any jumps. So here, when x is -2 at that transition point, I know my y value will be 4. So what I want to know is what would this point be? -2, what? Now, I know that this -2 is not defined for this function. I know that. We know that. -2 is defined for that top piece. But to decide if it's continuous, I need to see if those places match up. Does that make sense? Okay. So I know for this guy, it would be an open circle. But is that open circle going to be at the same place where we have this filled in circle? That's what we're looking for. So what I'm going to do is plug in -2 to this function. So it'd be -2 squared, which is 4. You see how those are the same? So where this is an open circle, this circle is going to fill it in. So we're continuous at -2. Now we got to check +2. So here on the graph, and this is the point that'll actually be on the graph, I have to plug in 2 to my function. That would give me 4. So I'm going to have the point 2, 4 on my graph. What I want to see is where this open circle is, 2, something, is it going to be at the same place? So is that open circle going to be filled in by the point that is actually on the graph? So 1/2 times 2 plus 3, plus 3. Half of 2 is 1. 1 plus 3 is 4. Same place? Yeah. So is this graph going to be continuous? Sure is. For C, is my graph going to be continuous? No, you don't even have to plug anything in here. How do we know it's not going to be continuous? It's not defined at 0. So we know we have a hole in our graph at x equals 0. There's a hole in my graph when x equals 0. Since it's not defined anywhere, I know it's a hole. If it were defined at one place or the other, I would have to check. And if they didn't match up, that's where I would have a jump. And then what about D? Mm-hmm. At 0 on B. No, that would be in this section, and it's okay to have 0 squared. Oh, for D, you mean? It's defined at 0 for this guy. So 0 would be in this part of the function, right? Is 0 squared undefined? Yeah. It's 0 on the bottom. 0 as a function value is okay. It's if it's on the bottom of a fraction, that's where it's a problem. Or in the argument of a log. And then for D. Where do I have problems on D? I've got all kinds of problems on D. Tell me some of them. 0 is a problem. We're undefined at 0. X cannot be 0. What happens when X is 0? That's an asymptote. Yeah. Vertical asymptote there. Where else do I have problems? At -2 and +2. What's going on at -2 and +2? Not quite. Are we defined at -2 or +2? Yeah, that's the problem. If I'm not defined there at all, that's a hole. Okay. If I'm defined, but it doesn't match up, that's a jump. If I'm not defined at all, it's a hole. So these are both holes. Last thing for today. Last thing with our piecewise functions. I would like you to try to change the underlined piece so that our functions would be continuous. And then on B, I will change the defined interval here so that we're including negative and positive too. I just want to change these so that they are defined. Okay, they are continuous, I should say. That means I want those pieces to match up. So if I look at my x squared piece at -3, this would be the point -3 comma 9, right? -3 squared is 9. So that means I want this to be the point -3 comma 9. Let's see what it is right now. So if I leave this function as it is, -3 times -3 plus 1, that would be 9 plus 1, which is 10. I have a lot of options here. I could completely rewrite this entire function, or I could adjust it a little bit. We're a little too big here, right? I want it to be 9, it's 10. How much did we overshoot it by? We're 1 too big. So what if we take our function and we just subtract 1 from it? If this is just -3x instead, would this be the point -3 comma 9? Yeah, it sure would. Could I write a completely brand new function there that's not even a linear function, that's something else entirely? Sure. Do I have to? No. For B, my function is 3 over x. And if I look at -2, that would be the point -3 over 2, which is not 4. And on the other end, I'd be at +3 over 2, which is also not 4. And I have an asymptote in the middle there. So I want something else that would be a continuous piecewise function. Okay. On this one, I'm not going to make a little adjustment. I'm going to completely scrap that underlying piece. And let's write something else. What's the easiest thing that I could possibly write? Yeah, I could just let it be 4. Arguably, is it a piecewise function then? If all the pieces are the same, maybe not. But I could just let it be 4. I could also let it be x squared because at -2, we get a function value of 4. And at +2, we get a function value of 4. So that would match up. For our last couple minutes, I want you to try and come up with one more option for what I could use instead in the middle there. So not 4 and not x squared. Come up with something of your own.